So what do we mean by states? Well, there's a number of ways that you can define states. Um, and uh, the key factor here is that animals can move among those states, and survival and detection probability may or may not differ among these different states. Some examples would be, say, locations of seabird breeding colonies where you have a number of islands or locations where species breeds, and there's a possibility that birds may move from one island to the next, and maybe survival or detection probability differs among those islands. And an important parameter you might want to know is what is the movement rate among those islands. Breeding status is another key state that's often examined with these models. If we're looking at sea turtles, for instance, you might look at turtles that come to the beaches on a particular year versus turtles that are staying away and are not breeding. And this could also refer to treatments. If you are applying treatments to individuals in populations, maybe in case of wild horses, you're applying treatments that stop mares from breeding. You might be interested in is there a difference in survival among those animals versus others in the population. In the multi-state model, we introduce a new parameter called psi, and that's a proportion of animals that move from one state to another. Key constraint on this parameter is that the values associated with a particular state must sum to 1, and I'll show you what that means in an example. And this addition of this new parameter now allows estimation of movement, survival, and capture probability separately in each one of these states. So for example, in this salmon that was studied in Japan by Kano et al., they were looking at the proportion of fish that moved among different locations within the river, from the lower portion, middle to upper, okay? And the numbers here indicate the values of psi that they found from their mark recapture analysis, okay? And in the case of the lower portion of the river, the fish that were there initially, about 86% stayed there from one time step to the next. About 7% moved from the lower to the middle, and about 7% moved from the lower to the upper, okay? So 0.86 plus 0.07 plus 0.07 equals 1. So that's what we mean when they sum to 1. You can confirm that for the other portions of the river. So if we go back to our typical mark recapture model, what we generally do is we go out, capture, mark individuals, and let them go. Then go out the next year and see, try to catch them again. And so we have two parameters. We have phi, probability of survival from this time step to the next, and p, the capture probability. Now what we're doing is saying that those animals not only can survive and be recaptured at that same location, but they could also move to another location. Okay, so in this case, the sum of those phis associated with a particular location will be equivalent to the survival of that animal in that metapopulation, or that population with multiple sites. So now, because we aren't always encountering the animals at the same site that we released them, we have to add some information to the capture history so we know where they were captured. And the way we do that is we use letters to designate the different states or sites or conditions, depending on what we're looking at. And then the 0, like it always has indicates that the animal was not captured on that particular trapping occasion. Okay, so AABOCC indicates that an animal was marked first at site A, the next year it was caught at site A, the third year it went to B, the fourth year it was not captured, and the fifth and sixth year it was caught at site C. So you can go through these other capture histories and see how they're described there, but it's pretty straightforward. And we can build capture histories and probability statements just like we did for the Cormac Jolly Seabird, where if we look at a capture history AOB, just like we saw with the Cormac Jolly Seabird, whenever you have an O in there, there's multiple ways that that can occur. So in this case, that animal was captured at site A initially. It could have stayed at that site, so that's why we have VAA, and then was not captured at that site, so 1 minus PA. It survived and moved to site B between periods 2 and 3, and then was captured at site B. Okay. Alternatively, that animal could have been captured at site A and then survived and moved to site B in that first year, was not captured at site B, and then moved to and then stayed at site B, so that's VBB, and was captured at site B at time 3. And we can do like we've done before, where we can combine these to come up with an expected frequency that we would expect this capture history to occur in our data set, where we could take RA sub 1, so assume we released, say, 100 animals at time 1 at site A, okay, then the expected frequency of this capture history AOB would be the number released times the probabilities associated with each of these parameters. So VAA times 1 minus P2 sub A, or superscript A. Okay, so that's probability that the animal stayed at site A, wasn't caught, and then moved to site B and was caught, plus the probability that the animal moved from A to B in that first year, was not caught at site B, and then stayed and survived at site B and was caught at that site on occasion 3. So as we talked about at the start, one of the key parts of this model is that you can separate movement and survival. And this again is pretty straightforward. So we've just been focusing on VRS, meaning probability of surviving from state R to state S at time I, and that can be decomposed into survival at site R. Okay, so the key here is that survival is always associated with the site where that animal was last captured. Okay, so we're assuming that either that animal stays there and then moves after, towards the end of the year before your next capture occasion, or maybe more realistically, that its survival across that interval is influenced by the conditions at that site where it was initially captured. Okay, so if there's something better about that, there's more food or whatever, then you might expect its survival to be dependent on where it was when you initially captured it there. We're using S here to indicate true survival. Again, if you have animals moving out, completely out of your metapopulation, then this would be equivalent to phi. We'll assume that we're looking at an entire breeding area for a species for right now. So we can decompose that into SR, indicating that survival is dependent on state R times psi RS, the probability of moving from site R to site S, okay, I indicating the time step here. So now we can see that the sum of those phi terms is basically equal to the annual survival, if we're using years, of this animal. And so the sum of all of those phi terms is equal to survival. Another way we can indicate that is if we're starting with site B, it would be phi BB plus phi BA plus phi BC would be equal to S, or survival across that interval for all the animals in the population. You can see the relationship between survival and movement if we look at this diagram now. And now we have separated survival and movement into S and psi. And so if we just look at site B now, the animal could survive and stay in B with SB psi BB, okay, that first term, or it could survive in B and move to A, SB psi BA, or it could move to C, SB psi BC. So if we just factor out the S, then we can see that this is equivalent to survival times the transition probabilities of all of those movements. And since we've defined that to be equal to 1, the sum of all of these transition and survivals is just going to be equal to the survival for animals in that state B. And so now we can look at both survival and movement. So we would have a survival associated with each one of these states, a capture probability associated with each state, and then a probability of either staying in that state, moving to, in this case, state B, or moving to state C. So you can just confirm that those movement probabilities are all going to sum to 1. And so just to kind of reiterate this, if you had a capture history BCACC, you can see each one of these terms has all of the parameters associated with survival, movement, and subsequent recapture probability. So if you start in B, you'll have survival associated with state B at time 1, your movement from B to C at time 1, and then capture probability where you end up at C. Okay. Same thing for this second step. You start in C, so it's survival associated with C, probability of moving from C to A, and then capture probability, recapture probability associated with that state A. Here we are with C, and notice for this last one where basically it's staying in C, one way of depicting transition probability here is just to refer to it as 1 minus psi CA minus psi CB, because again, those two plus probability of staying sum to 1. So that would be your probability of staying put. So as we talked about, when you input the data into MARC, you indicate with letters what those states are. In this case, we have 2 states, B indicating breeding animals, N indicating non-breeding animals, 0s indicating that animal was not caught on that occasion. So in this first line, we had 85 individuals that were caught as breeders in the first year and were never seen again. So you could either enter that as that capture history followed by 85, or you could have 85 rows, all with 1s at the end. And you have animals that are moving from breeders to non-breeder, breeding status, and so on. So when you bring the data into MARC, you have to tell MARC what these different states refer to. So in this case, you just kind of like when we define groups, you just indicate what B and N refer to in the two different states. And if we were to pull this into MARC then and just look at the most general model, what you'll see is along the y-axis here, you're going to have 6 different groups, right? You'll have S for your breeder, S for your non-breeders, probability of recapture for your breeders and non-breeders, and then movement probabilities from breeding to non-breeding status. And here we are estimating a different parameter for each of the time steps. And you're obviously going to run into some unidentifiability issues in this situation. A very simple modification of that most general model would be just to make all of the parameters constant across time for each of these different groups. So you'd have one value of survival for breeders, non-breeders, capture probabilities for breeders, non-breeders, and movement probabilities for breeders and non-breeders. And so, as we talked about, the interpretation of the parameters for S&P are similar to the CJS, where you have S for breeders, non-breeders, P for breeders and non-breeders. Psi, as we talked about, is probability of moving from one state to another. You can change this if your main focus is on the probability of staying put, then you can have MARC kind of indicate that initially and then calculate the probability of changing. Take a look at the MARC book. It talks about situations where you might want to flip that so that MARC is estimating the probability of staying put and then calculating the probability of moving based on that. In this case, it would just be 1 minus that value. If you are interested in setting up models in the design matrix, you want to think about how you set up your PIM before you then move to the design matrix. And so if you were wanting to look at the model where you had variation in survival over time, maybe capture probability and movements constant by group, you would set your PIM up like this, and then when you pull it into the design matrix, you would identify it as a reduced design matrix now with 18 parameters. And just focusing on the SG times T portion of this, again, take a look at the MARC book. You would want to set up your design matrix like this, where you have an intercept, a group effect, and then the time effect, and then your group by time interaction, just like we've done before. Once you set it up like this, then it makes it very easy to take out that interaction if you want to look at additive effects. So again, it just depends on where you're going with your model building. Another situation where these multi-state models are used a lot is when you have unobservable states. And you say, well, how can you do anything with unobservable states? Well, you make some assumptions, but you can actually get estimates of these same parameters. So for examples, with female sea turtles, they'll come in, nest on a beach, and then they may stay away and forage the next year and not come into the beach. Okay, there's no chance that you're going to see them in that situation. And so that foraging state would be a non-observable state. Same thing for long-lived seabirds, like these Laysan albatross. They'll breed, and then they'll often take a year or two off before they come back and try breeding again. So obviously, if you're banding birds on their nesting island, you won't see them during those periods. Amphibians, you know, they're up on the surface, moving, feeding, and then will move underground to where they're non-observable. So again, the biology of the animals indicates that there will be times when you know they're simply not observable. So what do you do? So if we look at the example of, say, sea turtle nesting beaches, if you think, okay, we've got animals coming into the nesting beach, we can estimate their recapture probability associated with nesting. We can estimate their survival and their propensity to come back to that nesting beach as a product of S sub n and phi sub nn. But then you think, well, the only other estimate we can come up with is probability of not surviving. But if we make an assumption, we can do more than that. And that is, if we set the probability of survival during that unobservable state being equal to the probability of survival based on the nesting state, now we can estimate the proportion that we use that nesting state survival to estimate the proportion that moved from nesting to unobservable, and we can use that to estimate, then we essentially get that probability of moving from unobservable to nesting. And notice in this unobservable state, we're using that assumption of SU equal to SN. One thing we would have to do, though, when we do the analysis, is we would have to set that probability of being recaptured during that time to 0, because obviously there's no chance of recapturing the individuals. So the way we would set this up in MARC is we would force the survival for the unobservable state to be equal to survival for that observable state. We would have a probability of recapture associated with that observable state, and that can vary from year to year. But we would have to set the probability of recapture for that unobservable state equal to 0, and we can do that in the fixed parameters part of the run window in MARC. And to just quickly review the assumptions of the multi-state models. So within each state, age, sex, and so on, all animals are equally likely to survive, move, and be detected. So no heterogeneity within those groups. Survival is a function of the state of origin, as we talked about, and movement occurs just before the capture period. Basically, survival is dependent on where the animal started. Marks do not affect survival or movement, not lost, recorded correctly. Each animal acts independently with respect to survival, movement, and detection. And where you can get into trouble with that is like long-lived bird species that might pair up. If they tend to move together in pairs, then obviously their movement, survival, detection are not going to be independent of one another. So in that case, you might just view a pair as a sample unit as opposed to each individual. And then state is correctly assigned at each time. Because we're meeting and going over your analyses this week, I am not going to make a assignment due for multi-state models. We've been throwing a lot at you, and so I want you to be able to have some time to put into working on your own projects. But I would recommend that you go ahead and pull up the deer.inp data and work through the example that they give you in the MARC book. These models are being used more and more, and so I think just being aware of them and how they work would be important. I am not going to require that you run multi-state models on the midterm.